We've learned about translations and reflections in the previous lessons. Today, we're moving on to rotations. A rotation is when a figure moves in a circular motion around a point. Sort of like how Mia's turning around this blue point here. Before we go any further in this video, you'll need to complete the Satellite Simulations Part 1 activity that comes before your guided notes. If you haven't done that yet, pause the video now and come back when you're finished. Great! Let's get started. In this course, the origin will be the point of rotation. Let's use this Mia to demonstrate rotation around the origin. Remember, the origin is like the center of a fan, and Mia is like a blade of that fan. Each part of Mia, like this point on the tip of Mia's antenna, will always be the same distance from the origin. As Mia rotates around the origin, maintaining the same distance, the movement naturally follows the path of a perfect circle. This is in the clockwise direction since it's in the direction of a clock. Rotating Mia the other way, like this, is in the counterclockwise direction. A full rotation around the origin is a 360-degree rotation, where Mia does a full lap around the origin before returning to its original position. In this course, we'll only focus on rotations in 90-degree increments. Let's take a closer look. Since 360 degrees divided by 4 is 90 degrees, that means if Mia rotates a fourth of a full rotation like this, that's a 90-degree rotation. Let's also specify that the rotation is in the clockwise direction. What if we rotate Mia clockwise half of a full rotation instead? How many degrees rotation would that be? Since this is half of 360, this is a 180-degree clockwise rotation. We can also see that this is 2/4 of 360 degrees, or simply 2 90-degree clockwise rotations combining to create a 180-degree clockwise rotation. If we rotate Mia clockwise 3/4 of a full rotation, like this, how many degrees would that be? Since that's 3 90-degree clockwise rotations, that equals a 270-degree clockwise rotation. And finally, a full 360-degree rotation would rotate Mia all the way back to its original position. Great! Let's reset this so we can look at counterclockwise rotations. Going in the counterclockwise direction, this is a 90-degree counterclockwise rotation, a 180-degree counterclockwise rotation, a 270-degree counterclockwise rotation, and finally, 360-degree counterclockwise rotation, back to the original position. Wait a minute. Aren't these images identical to the images produced from the previous clockwise rotations? Let's compare them side by side to make sure. Comparing the images created by clockwise and counterclockwise rotations, we see that the same images were created. Even though we rotated Mia in opposite directions, both paths resulted in the same image. For example, a 90-degree clockwise rotation and a 270-degree counterclockwise rotation both create the same image right here. What's a similar example? What clockwise rotation would create the same image as a 90-degree counterclockwise rotation? A 270-degree clockwise rotation would create the same image. And finally, for 180-degree rotations, Sometimes we don't specify whether the rotation is clockwise or counterclockwise. 180-degree rotations create the same image regardless of direction. Let's reset these images and merge them together for an overall summary. And here it is. So, we know how clockwise and counterclockwise rotations work, but what about actually performing these rotations? Without a ruler or protractor, it'll be pretty difficult to eyeball perfect 90-degree rotations. Oh, I know! Let's only focus on these points to see whether there are certain patterns in how their coordinates change. This will help us figure out the coordinate notations of different rotations. For this section, make sure you fill in this table in your guided notes. It'll help summarize the coordinate notations of each rotation. Let's rename the pre-image as point M. To figure out the coordinate notations, we need to first find and compare the coordinates of these points. Go ahead and find the coordinates for all 4 points. Pause now. And here are the coordinates. Notice anything about the numbers in each of these coordinates? It looks like the coordinates use the same numbers, but the x and y coordinates may have switched places, or they may have different signs. Interesting. Let's take a closer look at how the coordinates change. When pre-image M rotates 90 degrees clockwise or 270 degrees counterclockwise to create image M prime, we can represent the transformation from the pre-image to the image like so. How do the x and y coordinates change? Are the x and y coordinates in the same place? The x and y coordinates actually switch places. The original x-coordinate 2 is now the new y-coordinate, and the original y-coordinate -4 is now the new x-coordinate. So far, the coordinate notation looks something like this. But wait, the 2 actually becomes its opposite, a -2. To represent that change, we can add a negative sign next to the x value in the new coordinates. The negative sign here does not literally mean that value is negative. It simply means the original value has become its opposite. This is the coordinate notation we can use to perform a 90-degree clockwise or 270-degree counterclockwise rotation. Now let's look at a 180 degrees clockwise or counterclockwise rotation. We can represent the transformation like so. How did the x and y coordinates change? The x and y coordinates stayed in the same place, but both coordinates became their opposites. 2 became -2, and -4 became +4. What would the coordinate notation be? Pause the video now to complete it. Here's the coordinate notation where the x and y coordinates are in the same place, but are now their opposites, represented by the negative signs. This is the coordinate notation we can use to perform a 180-degree clockwise or counterclockwise rotation. Finally, let's look at the transformation for a 270-degree clockwise or 90-degree counterclockwise rotation. Based on how the coordinates change, write the coordinate notation. Pause now and resume when you're ready. Since the x and y coordinates switched, we can write the new coordinate as y, x. Do we need to include a negative sign somewhere? Since the original y-coordinate -4 becomes its opposite, +4, the y needs a negative sign. This is the coordinate notation we can use to perform a 270-degree clockwise or 90-degree counterclockwise rotation. Here's the completed table summarizing the coordinate notations of each rotation. Feel free to pause now to compare your notes. These coordinate notations allow us to understand how coordinates change after rotations, and we can use them to perform the rotations ourselves. Let's apply what we've learned to two example problems. Pre-image point G is at -4, -3 on this coordinate plane. We want to find and plot the coordinates of the images after a 90 and 180-degree clockwise rotation. Let's do the first one together. What does the coordinate notation of a 90-degree clockwise rotation tell us to do with the x and y coordinates of the pre-image? It tells us that x and y coordinates of the pre-image will switch, and the original x-coordinate would become its opposite. Let's apply that to our pre-image coordinates. What would the new coordinates be? We'll switch the coordinates, and since the opposite of the original x-coordinate, -4, is +4, we can expect our final coordinates will be -3, +4. Let's plot that and label it G prime. Looking at this point, we know that it's correct because it's in the clockwise direction. It's the same distance from the origin as point G, and they create a 90-degree angle. Okay, want to give it a shot? Find and plot the coordinates for a 180 clockwise rotation. Pause now. Here's the coordinate notation for a 180 rotation. It tells us that the x and y coordinates remain in their places, but they both become their opposites, giving the final coordinates of 4, 3. Plotting it, we can see that it's also the same distance from the origin as point G, and they form a straight angle, which, as we learned from the last unit, measures 180 degrees. Okay, next problem. Plot the image of triangle RST after a 90-degree counterclockwise rotation. What's the equivalent clockwise rotation to that? Yeah, a 270-degree clockwise rotation would result in the same image. You may pause now and come back once you're finished. Here's the coordinate notation for the rotation and the original coordinates. Using the coordinate notation, we switch the x and y coordinates, and the original y coordinate becomes its opposite, giving us the new points, and plotting them creates the new image. This is indeed a 90-degree counterclockwise rotation, or a 270-degree clockwise rotation. And before you know it, you've mastered the final rigid transformation of rotation. Check out the rotation strategies page after your guided notes, and then jump into some practice levels. And remember, math is everywhere. Keep exploring. Hey, hey.